Have you ever seen a science headline and just wondered, how on earth did they prove that? Well, it's not magic. It's all about statistics. And today, we're going to pull back the curtain and show you exactly how researchers make those calls.
I mean, this is the central question in any research, right? It's never enough to just spot a pattern. You have to prove it wasn't just a random fluke. And the key to that proof is using the right statistical test. But, and this is a big but, there are dozens of options, and choosing the right one can feel totally paralyzing.
And hey, don't just take my word for it. Researchers themselves call it a daunting task. That's a direct quote from the very paper that inspired this whole explainer. But here's the cool part. They didn't just point out the problem. They actually laid out a super clear, simple way forward.
So here's our game plan for today. First, we'll talk about why this is such a daunting problem. Then we'll walk through their simple two-step solution. That's knowing your variables and knowing your goal. From there, we'll put it all together to find the right test. And finally, we'll cover the common pitfalls you really need to watch out for. So, how do you solve a problem that feels, well, daunting? Simple. You break it down into smaller pieces. And that's exactly what the authors of our source paper did. They came up with this really elegant, almost algorithmic way to cut through all the noise. And get this, it all boils down to answering just two key questions. Yep, that's it. Just two. Think of it like you're cooking. The first question is, what are you measuring? These are your ingredients, your variables. And the second question, how are they related? This is your recipe, your ultimate goal. If you can nail these two things, you've pretty much cracked the code. All right, let's dive into step one, getting to know your variables. And to make this super clear, we're going to use a running example straight from the paper. We're going to investigate the possible link between having a history of sunburns and the number of moles a person has. Okay, so first up is what's called the outcome variable. The easiest way to think about this is that it's the effect. It's the thing you're trying to explain or predict. So in our sunburn example, what are we trying to explain? The number of moles a person has? Boom, that's our outcome variable. Right, so if the number of moles is the effect, what's the potential cause? Well, that's your explanatory variable. Our hypothesis, our educated guess, is that a person's history of sunburn might explain why some people have more mole than others. It's the thing we're testing to see if it's the driver. But hold on, it's not just about identifying cause and effect. The kind of data you have is hugely important. So you have to ask, is your data categorical? Meaning, does it fit into neat little boxes, like a yes or no for having a sunburn history? Or is it continuous? This is more like a measurement on a scale, things like age or the exact number of moles, where the differences between numbers are really meaningful. And you know, the type of variable you're working with directly tells you the best way to summarize it. For data that's all nicely spread out, what statisticians call normally distributed, the average or the mean works just great. But if your data is skewed with a few really high or low values throwing things off, the median, that's the middle value, is actually a much better, more honest snapshot. And for simple yes or no data, well, you just need a proportion or a percentage. All right, so we've got our ingredients sorted, our variables. Now for step two, the recipe. In other words, what are we actually trying to do with all this data? What's the fundamental question we're trying to answer? So the paper suggests it really comes down to one of three main goals. Are you just looking for a correlation? You know, do two things seem to move together? Or are you looking for a clear difference between groups? For example, do people with a history of sunburn have more moles than people without? Or maybe you're digging for a more complex association where you might have to adjust for other factors. Okay, this is the moment. This is where the magic happens. We've got our ingredients, the variables, and we've got our recipe, the goal. Now we're going to put it all together and find the absolute perfect statistical test for our question. And the best part is, the authors didn't just throw these concepts at us and say, good luck. Nope, they gave us a map, a cheat sheet really, a tool that takes all of the guesswork, all of that anxiety right out of the equation. And here it is. This simple little table is the absolute heart of their entire method. Seriously, it turns what feels like a super daunting decision into a simple lookup game. All you do is find your outcome variable type along the top, find your explanatory variable type down the side, and then see where they meet. The box where they intersect? Yep, that's your test. It's that simple. Okay, so let's use our running example to see this in action. Our goal, remember, is to see if there's a difference. Our outcome variable, the number of moles, is continuous, but it's skewed. And our explanatory variable has just two groups, sunburn history or no sunburn history. So we just follow the grid, and bam, it points us directly to something called the Wilcoxon rank sum test. No guessing, no stressing. The table just tells you.
Okay, so this two-step framework is an incredibly powerful starting point. It's a game changer. But the real world is messy, right? Real data is never that clean. And the paper is really good about highlighting some of the most common traps that researchers absolutely have to watch out for. Think of these as the big four pitfalls. Each one of them is a potential landmine that can lead you to a totally misleading result. You have to ask yourself, are my data points actually independent? Is there some hidden third variable that's secretly driving the results? Does the effect I'm seeing change depending on the group I'm looking at? Or did I just test so many things that I was bound to find something significant just by pure chance? Let's zoom in on what is probably the most common trap of all, confounding.
A confounding variable is basically the ultimate third wheel in statistics. It's this outside factor that you might not have even thought about, but it's connected to both your suspected cause and your observed effect. And by doing that, it can create the illusion of a direct link between the two, totally biasing your results.
Here's a classic, perfect example to make this stick. Say you run a study and find a strong link between tanning bed use and melanoma. Case closed, right? Well, not so fast. What about age? We know that older people might have been more likely to use tanning beds back in the day, and we also know that older people are naturally at a higher risk for melanoma just because of their age. The question becomes, is the tanning bed the real culprit, or is age the confounder here, the hidden variable that's actually explaining the whole pattern? And look, navigating tricky issues like confounding is exactly why the authors end with this piece of crucial advice. This framework we've walked through is an amazing guide. It's a fantastic first step to get you on the right path. But when the data gets messy, and it almost always does, the smartest, wisest thing you can do is talk to an expert, like a biostatistician.
So, what does this all mean for you? Well, the next time you're scrolling and you see one of those headlines that says, "New study proves X causes Y," you're going to have this brand new lens to look through. You can start asking the right questions. What were the variables? What was the actual goal of the study? And, maybe most importantly, were there any potential confounders that might be skewing the results? See, understanding this logic doesn't just make you sound smart. It makes you a more critical, more empowered, and way more informed consumer of science.